Hello Year 10 and welcome to the end of year exam foundation walkthrough. So I'm going to go through the answers and then there'll be some follow-up questions for you to complete in a Google document. So let's make a start. There are many energy resources, which two are renewable? So coal and gas are fossil fuels, it cannot be that. Nuclear technically is not a renewable resource, it will run out because we're still using a fuel once it's broken down, also once it's decayed, it's over. So these are the only two. Geothermal is when we pump water down into the earth, then it heats up and we can turn turbines with it. And biofuel is where we grow crops and then we turn those crops into some kind of fuel. Part B, which describes a reliable resource. So the key word here is reliable. So reliable does not mean that it doesn't burn fuel. It doesn't mean that it will run out. It doesn't mean it's cheap. It means that it's predictable. Okay, we know exactly how much we're going to get when we get it. Part C, tick one box. The total power output of the wind farm is 19.6 megawatts. What is the power output of one wind turbine? Okay, so what do we need to know? All of them have the same output. That's good. And we also obviously need to know how many wind turbines there are. Well, that's okay. We can count them up. 1, 2, 3, 4, 5, 6, 7. So the total output is 19.6. So that's 7 of them. So if we divide it by 7, we get the answer for 1, and that's 2.8. Okay, so it's not always obvious you have to count in a picture, but if you use your common sense, that's what you have to do. Part D, why might people not like having wind turbines near their homes? Well, I don't agree with this, but some people think that they are eyesores, right? So visual pollution, they just don't like the look of them. And some people say that they are noisy, so noise pollution. And some people say that they are dangerous to birds, so they don't like having them anywhere. Right, but these are the two main ones. Okay, they don't look very nice and they're noisy. I don't agree with them. I think they look beautiful, but that's not what everyone thinks. So here, explain the environmental impacts of the changes. So what are the changes? Well, we've got this pie chart from 2014, this pie chart from 2015. What are the changes? So let's have a look. So let's go around in turn. So gas, there is no change. It's 30%, it's 30%. Nuclear 19 to 21, coal 30 to 22, renewables 19 to 25. So the main things we're going to start with is in 2014, coal was 30%. In 2015, coal reduced to 22%. Okay, so this means that we're burning less coal, so there is less carbon dioxide being released. And there's going to be less pollution in general. Okay, so less pollutants, things like sulfur dioxide, or less smog. What's the other big change? Renewables have gone from 19, have gone from 19% in 2014 to 25% in 2015. So this is obviously better for the environment because there is less CO2 being released and no pollution at all. Gas we can't say anything about. Other fuels we can't say anything about because it hasn't changed. The last thing is nuclear. So nuclear has increased by 2%. Nuclear isn't really bad for the environment, but I guess you could say there is a small increase in risks, or in the risk of a nuclear explosion. Okay, it's a very, very tiny risk, but if it's increased a little bit, then that risk has increased a tiny bit as well. Okay, question 2. Figure 3 shows a mobile phone being recharged by a portable power source. Why does the battery in the phone need recharging? So let's have a look. So the store of chemical energy in the battery has reduced. That sounds very reasonable. Let's check the rest of them. The store of thermal energy in the battery has reduced. Well, that's just rubbish because we don't want batteries to get hot. The store of kinetic energy in the battery, although there's no kinetic energy in the battery, there's no movement. And the store of gravitational energy in the battery, well, the battery doesn't store gravitational energy, because it's not being kept up high. So it must be the first one. There is a chemical store in the battery that reduces. The power source provides a current of 1.6 amps at a potential difference of 3.9 volts. Calculate the power. It's given us the equation here. Power is potential difference times current. So we need to take the potential difference, 3.90 volts, and we need to times it by the current, 1.86 amps. And that's going to give us 7.25. And then watts is the unit of power, so W. If you didn't put W, you would lose a mark because it says to do it. A student needs a new power source. Figure 4 shows 3 different size power sources. Table 1 gives data about the different power sources. Okay, we've got compact, large, and high capacity. We've got their charges and their mass. And then it says the student chose the large power source. Suggest why the student chose the large power source. So there's 4 marks here. So we need to say either 4 things or something that's sufficiently detailed. So you might think, well, why not just go for the high capacity one? It gives more charges. But then obviously we need to take in the mass as well. So let's kind of do a calculation here. Let's have a little think. So compact, okay, 1 charge corresponds to 100 grams. Right, the large, 5 charges is 200 grams, which means that 1 charge corresponds to 40 grams. And the high capacity, we've got 10 charges is 600 grams, so 1 charge is 60 grams. So actually, looking at this, which is the kind of most efficient? Which has the lowest mass per charge? Well, the large has the lowest mass per charge. You could say ratio. So actually, it's kind of more efficient. It stores the most charge for the same amount of mass. So if you want something that's kind of efficient and compact, the large is actually better than the high capacity one. So this on its own would actually get you all 4 marks. Question 3. Figure 5 shows a girl skateboarding on a ramp. Girl has a mass of 50 kilograms. Use this equation to calculate the gravitational potential energy. So this is super easy. GPE is mass. The mass is 50 kilograms. Gravitational field strength is 9.8. Tells us here. And the height, well, we can get it from the picture, is 4 meters. So let's put that into our calculator. 5 times by 9.8 times by 4 is 1,960. It's energy, so we can put joules. Okay, we're going to work out the kinetic energy this time. So the kinetic energy is 0.5 times by 50, and then times by the speed squared. So 7 squared. Well, we can just write 7 squared as 7 times 7 like this. Fancy. So let's put that into our calculator. We get 1,225 joules. Super easy. Part C. Not all of the GP has been transferred to kinetic energy. Which 2 statements explain why? So some energy is wasted. That sounds reasonable. The mass of the girl is too low. Well, that's just irrelevant. Doesn't matter. It's not going to talk about. That's nothing to do with waste. The ramp is not high enough. Nothing is. I mean, I don't think that's really relevant. The GPE of the girl is not 0, or the speed of the girl is too great. So the speed of the girl is too great doesn't explain anything. The ramp is not high enough doesn't explain anything. This one here does explain something. So not all of the GPE has been transferred to kinetic energy. Well, if not all of the GPE has disappeared, then that's true. Then that makes this true. So maybe at the bottom of the ramp, well, we can see here, can't we? She's still a height above the ground. And if she's still a height above the ground, then she still has some GPE, gravitational potential energy. And you can imagine if like there was another little side bit of the ramp that went down to the ground, she could still lose more gravitational potential energy. Final part of this question. Explain how lubricating the wheels of the skateboard can increase the speed of the girl. Use ideas about energy in your explanation. So importantly here, it's about the wheels. If you have to talk about the wheels, otherwise you won't get all the marks. So lubricating the wheels means less energy is wasted as thermal. That's heating the wheels. More energy is transferred to the kinetic store of the skateboard. Right? And why is that? Because lubricants are smooth and slippery. They reduce friction. So we reduce friction, less energy is wasted as heat, more goes to the kinetic store. So an answer like this gets you all 3 marks. Question 4. Suggest why some ceiling lights do not have an earth wire. And here we've got a picture of a ceiling light that does not have an earth wire. So you have to remember that an earth wire is for safety, and it provides a short circuit in case there's a problem, in case one of these wires touches the light. However, if the light is made of plastic, the plastic will not conduct electricity. No earth is needed, as there is no danger of electrocution. Okay, so really just this bit actually is probably enough. Right, light could be made of plastic. Write down the equation that links charge flow, current, and time. So charge flow equals current times time, or in symbols, Q equals IT, but you would always write it in words. You don't write it in symbols. You always write whatever's in the question. So we're going to use that equation to calculate the answer to this. So charge flow is current times by time. On our calculator, we get 177 coulombs. Now we've got a question here. What circuit component does this graph represent? So we've got voltage, we've got current. They're directly proportional. That is true if it's a resistor. If it was a curved line, it might be a bulb, like an S shape. And if it was a kind of straight line and then increased, it would be a diode, but this is a resistor. What is the name of the relationship between current and voltage in the graph below? They are directly proportional. Okay, straight line through the origin is directly proportional. What's the correct symbol for a fuse? The answer is B. Describe how the movement of the copper particles in the wire changes when the copper melts. So this isn't really an electricity question. This is a thermal question, really, or almost a chemistry question. So as the wire melts, the particles break their bonds. They are more free to move around or slide past each other, and they are no longer in fixed positions. Okay. As the wire melts, the particles break their bonds. They are more free to move around or slide past each other, no longer in fixed positions. Okay, calculate the energy needed to melt 500 kilograms of copper at its melting point. Tells us the heat of fusion of copper. It says use the physics equations used. So we need to use energy is mass times by the latent heat. So 500 kilograms times by 200. We've got to be careful here. We don't want to just put 200 in because this is kilojoules. We want it in joules, so 200,000 joules. That is our working out. Type that in, make sure we put enough zeros in, and we get 1 with 1, 2, 3, 4, 5, 6, 7, 8 zeros. So I'm going to write that as times 10 to the 8, like this, 10 to the power of 8. You would obviously write that in standard form. You could write 1 with 8 zeros. That would be fine as well. Question 5. Radionuclei can emit alpha, beta, or gamma radiation. Which type of radiation is the most penetrating? Penetrating means it can get through the most stuff. Gamma can get through the most stuff. It's only stopped by really thick metal, like lead, or really thick concrete. Which type of radiation is the most ionizing? So ionizing means it can add or remove electrons. Therefore, something that's very charged will be ionizing. That's alpha because it has a +2 charge. What has the longest range in air? Gamma. Gamma has an infinite range in air. Okay, now we've got a decay equation here. So we've got uranium is turning into these other two things. And it says, show how many neutrons and protons there are. So firstly, what is A? Well, A is about uranium. Uranium, it tells us the number of neutrons, how many protons. Well, when we look at uranium, or we look at this number, it's got a really big number here. This is the mass number. This is the protons and neutrons added together. So if we just want the protons, we need to take away the neutrons. So we can do 238 minus 146. So what does that equal? 238 minus 146. That's 92. And then B, again, 234 is the mass number. Take away 90. That gives us our number of neutrons. So that gives us 144. Part E, the nuclei of some isotopes are radioactive. Which of the following statements could apply to a radioactive nucleus? It doesn't emit sound, that's rubbish. Does it emit light? Well, it's a little bit vague that. Will it emit an atom? They never emit atoms. The only one that's left, it could emit a neutron. All right. A little bit of a trick question there because we haven't really talked about this in too much detail, but it can't be any of these three because they're just nonsense. So it must be this one. Give one similarity and one difference between the nuclei of potassium-40 and calcium-40. So what's happening is that potassium-40 is a radioactive isotope. It shows how potassium-40 will decay into calcium-40. So let's look at the differences and similarities. Well, the mass number, the big number, is the same in each. It has the same total protons and neutrons, but let's look. The atomic number is different. Okay, it's 1 higher than calcium. So what does this mean? So calcium has 1 more proton than potassium, but they have the same total protons and neutrons. The activity of a sample is measured 3 times. The measurements are given below. Which of the following explains why the readings are different? Well, that's because radioactive decay is random. It means you can't predict it. Every time you do an experiment, it will be very slightly different. Just like every time you roll a dice, you will get different numbers. Okay, use the figure above to determine the half-life of potassium-40. So half-life, the time it takes for half the atoms to decay. So we start here, we go down by half. So what number is this? This is about 1080. So half of that is 540. So that's about here. So we go across, we go down, and we get to about here, which is about 1.4 billion years. When food is eaten, some of the radiation the food emits is detectable outside the body. Which type of radiation would not be detectable outside the body? Alpha would not be. Alpha gets stopped by paper or skin. So if it's inside your body, it can't get out. You won't be able to detect it. Question 6. We've got 2 models of the atom here. What are the correct words? So let's start with the nuclear model because that's probably easiest. Right, the bit in the middle of the nuclear model, which is C, is the nucleus, and the bit around the outside, they're electrons, but the arrow is not actually pointing to an electron, is it? It's pointing to the circle or the ellipse. It's pointing to the orbit of the atom. Part A, what have we got? We've got A is pointing to the negative thing. The negative thing in an atom is the electron. And what is B? Well, we didn't know that there was a nucleus. We just thought it was the atom. Right? The whole thing is the atom with some electrons stuck on. Only later on we discovered it actually is a nucleus with orbits. Explain why the total positive charge in every atom of an element is always the same. Because all atoms of the same elements have the same number of protons, and protons are positively charged. Results from the alpha particle scattering experiment led to the nuclear model. Alpha particles were fired at a thin film of gold at a speed of 7% the speed of light. Determine the speed of the alpha particles. It tells us the speed of light here. So we want 7% of this. So we times it by 0.07, or we times it by 7 and we divide by 100. Okay, maybe I'll put it like this so you can see. So now we type all that into our calculator. We get 210.12312 meters per second. Figure 2 shows two atoms represented as solid spheres. A hydrogen atom has a radius of 2.5 times 10 to the minus 11. Determine the radius of our magnesium atom. So in the actual exam, it was there was no ruler here. You had to use your own ruler and you had to measure it. But here, I've put a ruler on so you can use this ruler to help you. So the hydrogen atom is 2.5 times 10 to the minus 11 meters. And what does that correspond to? That corresponds to 0.9 centimeters. Okay, what about the magnesium atom? Well, this is 8 minus 2.6, which is 5.4 centimeters across. Okay, so how many times bigger is it? Well, it's 5.4. The hydrogen atom was 0.9, so it's this many times bigger. It's 6 times bigger. So our answer is going to be 6 times 2.5 times 10 to the minus 11. Do that, 6 times 2.5 times 10 to the minus 11. That gives us 1.5 times 10 to the minus 10. So this is your answer here, 1.5 times 10 to the minus 10. Question 7. A student wanted to determine the density of the irregular shaped object shown in figure 3. Plan an experiment that would allow the student to determine the density of the object. So this is just like in the revision lessons. So if you did those, you should got 6 marks in this. So density is mass divided by volume. Mass can be measured using a mass balance. Volume can be measured by filling up a beaker of water, or you could say Eureka Cam, right to the top, put the object in and collect any water that spills out using a measuring cylinder. And then we know that 1 milliliter is 1 centimeter cubed. So now we have the volume, and because of that, we can use this equation here, density is mass over volume. So just this on its own would get you 6 marks. Okay. 1, 2, 3, 4, 5, 6. Okay. Part B, determine the uncertainty in the student's result. So uncertainty is half the range. So what's half the range? 1120 minus 960, which is equal to 160, and then 160 divided by 2 equals 80. So the uncertainty is 80. So it could be 1040 plus 80, 1040 minus 80. Be our range of answers. Question 7. What is the missing number? So again, another super easy question. We've got the mass number. We want just the number of neutrons. We take the mass number, 131. We take away the number of protons, and we get 78. That is our answer. What's the missing word? The number of protons in an atom is the proton number or the atomic number. An atom of iodine 131 decays into an atom of xenon by emitting a beta particle. The decay of iodine 131 can be represented by the equation below. Calculate the equation by writing the correct number in each of the two boxes. So we need to know that a beta particle has a naught on the top and a -1 on the bottom. It's an electron, so it's no protons or neutrons, but it's got -1 charge. So that means that A is 131 minus 0, or 131, and B, well, it's 53 minus -1, or 54, because if there's a -1 on the bottom, what number -1 is going to be 53? It must be 54. Almost at the end. Complete the following sentence. To run up the stairs, the student must do work against the force of, super easy, gravity. The student did 2,240 joules of work going from the bottom of the stairs to the top of the stairs. The student took 2.8 seconds to run up the stairs. Calculate the power the student developed. It's a funny wording that. It just means calculate the power. So power is the rate of transfer of energy, or energy divided by time. 2,240 divided by the time, 2.8. Put that in our calculator and see what we get. We get 800, and of course it's watts for power. How much gravitational potential energy did the student gain going from the bottom to the top of the stairs? We probably need to look up to the previous questions here. So here it says the student did 2,240 joules of work going from the bottom of the stairs to the top. So where has that work gone? It's gone into gravitational potential energy. So whatever energy they used, that's all gone into gravitational potential energy. Part C. Another 4 students did the same experiment. The measurements taken and the calculated values of the power were given in the table. To make a fair comparison of the students' to make a fair comparison of their powers, the students kept one variable in the experiment constant. What variable the students keep constant? So it can't be something that's in this table. It has to be something else. They obviously kept the height of the stairs the same, because it wouldn't be fair if they were running a different height. From the data in a table, the student wrote the following conclusion. The greater the weight of student, the greater the power developed. Why is this conclusion not true for a larger group of students? Because some students might be quicker or slower. Really? I mean, we can see it. It's sort of true here, isn't it? This student weighs more, but they've got a lower time. Because some students might have quicker or slower times than other students. All right, it's only true for 4. All right, and we've only got a very small sample size. Question 9, I think this is the last question. Calculate the total resistance of the 2 resistors, and it tells us that 2 resistors are joined in series, so it's super easy. Resistance always increases in series. So add them together and get our answer of 35 ohms. Part B. Calculate the reading on the voltmeter. The circuit was set up as shown in the diagram. The 3 resistors are identical. That's really important. So if this is 6 volts and they're all identical, they will each get 1/3 of the volts. They will get an equal amount of volts. They will all get 2 volts. The same circuit has now been set up with 2 ammeters. Pick the correct answer from the box to complete the sentence. The reading on ammeter A2 will be equal to the reading on ammeter A1, because current is the same everywhere round, right? It's the electrons flowing around So you have the same amount of electrons at all the different points in the circuit, so the current will be equal. Part D. So this is all about definitions. So do you know your definitions? So the current through a resistor depends on the potential difference across the resistor. A direct current only goes in one direction, and that is supplied by a cell or a battery. In a series circuit, the potential difference is shared by the components, just like we saw in that previous question. An alternating current is constantly changing direction, so that must mean that in a parallel circuit, the potential difference across each component is the same. Being very slow. I'm pretty sure this is the last question. So what you can do now is to complete the follow-up questions in the Google document that your teacher has provided.